everyone. We're going to go over section 5.1 today, exploring probability. Most of this is going to be introducing some terminology that we're going to use throughout the chapter. So we're going to begin with trial, which is just anything where you don't know the outcome for sure. So for us, it will be tossing a coin, rolling a die, or picking a card out of a deck of cards, something along those lines. Next up is experiment. And an experiment is just when you combine one or more trials together. So let's say you draw two cards in a row, or if you toss a coin and then you roll a die. So it makes it a little bit more complex. So a single operation is a trial, one or more is an experiment. Next up is an outcome. This is a kind of an important one. So an outcome is one of the things that could happen. So for example, if you flip a coin, you can end up with heads or tails. So that's this first one here. Generally, instead of writing heads, we're going to write H. Let's say, for example, the second one, this is more likely to be an outcome for, let's say, rolling two dice. Let's say you roll two six-sided dice, you get a 6 and a 4. That's a possible outcome. Likewise, T is for tails, of course. So you have heads and tails. And again, we're not going to write this out every time. And then this would be two dice maybe. And then, oh, actually, sorry, this would be tails and then a 4. So I think the experiment here would be um, tossing a coin and then rolling a single die. Next up is sample space. So sample space is a list of all the possible outcomes. So if you flip a coin, you can have heads or tails. So those are the two possible outcomes, and this is complete sample space. Now, whereas you have 1, 1, 1, 2, and so forth, all the way up to 6 and 6. So this would be something like two dice. And in this chapter, if we don't say anything about like what kind of dice they are, then we can assume they're standard six-sided dice, 1, 2, 3, 4, 5, 6 being the faces. So finally, the last part, this will be coin and die. And sometimes you'll be able to figure out what the experiment was based on the sample space, but not all of the time. But so coin and die. So a sample space is all of the possible outcomes. Emphasis on the word all. An event is a selection of those. You can pick all of them, but usually you'd be like, okay, so the event that I want when I flip a coin is I want heads, for example. So that will be an event. Or you can roll two dice and you want a 1 and a 4. The first one to be a 1, second one to be a 4. So that's a possibility. And then finally, the last one will be tails and a 2. So these three events are from the sample spaces from the previous part. Okay, so the idea here is you need to know how many things there are in the sample space and how many events that you want to happen. And that's how generally we determine probability. So if you look at what it says under probability, okay, it's a little bit more complicated because the entire chapter is about probability. So it says to denote the probability of an event A, and again, that is a selection of outcomes that we like. Uh, so we write P of A, probability of A. And probabilities are usually represented as decimal or fraction between 0 and 1. Now, something that never happens would have a probability of 0, and something that always happens will have a probability of 1. So it cannot be more than 1, it cannot be less than 0. So let's say, so something that would have a probability of 0 would be rolling a 9 on a standard die. So if it's six-sided die, 1, 2, 3, 4, 5, 6, you cannot roll a 9, right? So, and you can have events that always happen. So you can roll a die and Uh, you want a number that's a natural number less than 7. So 1, 2, 3, 4, 5, 6 are all natural numbers less than 7. So that's guaranteed to happen. So this never happens, the first one. Oops. Never happens. And then the second one always happens. So, and of course, probability is not so much about things that never happens or always happens, it's about everything in between. So usually they will be some kind of a proper fraction for us. Okay. And the last one is what's known as complementary events. So they are an event and then the complement if their probability adds up to 1. So this would be, let's say, first event is heads, which is 50% of the time you flip a coin and um, get heads um, on a fair coin, plus the probability of tails, the other 50%, that will add up to 1. So they are known as complementary events. And of course, we can make more complicated complementary events depending on our sample space and what implements we're using and so forth. So the next step, this is the kind of an important part. We are going to base our studies off of just experimental probability. We're going to learn to calculate these things. So the formula, if you will, of probability of event A is the number of outcomes favorable to A and then the total number of outcomes in the sample space. So nice and easy one would be the probability of heads that we had earlier. One side of the coin is heads. There are two sides of the coin, and they're both equally likely, so you get a half. Okay, so we're gonna have more examples of events that are like created by ourselves. So look at this one right here, example number 1. It says 4 black counters and 5 white counters are placed in a bag, and then we draw a counter at random. So the probability that the random counter is black would be probability of a black counter, and then that will be there are 4 favorable outcomes, and that is the ones we want. And then this will be divided by, quite simply, 4 plus 5. So you will get the probability of 4 over 9. So that's it. Now, because there's only 2 colors of counters in the bag, if the selected counter is not black, then there are 5 counters that are not black. So this would be 5 out of 9. So nice and easy one. So you can see in this case that the selected counter is not black and the selected counter is white are the same event, so they're equivalent. Okay. So we're not going to talk a lot about experimental probability in this chapter. So basically, experimental probability is just if you actually do something a number of times and see what happens. So it says here, if you roll a die 10 times and record the number of fives, you get what's the experimental probability of getting a 5. So the theoretical probability, which you by now should know how to calculate, the probability of a 5, there's 1 5 on the die, and there are 6 sides. So the theoretical probability is 1 over 6. The experimental probability, well, that will be a case by case thing, right? So you might get really lucky or unlucky, and you'll roll a die 10 times, and you might have like 8 fives, or you might have like 2 fives, right? So that's the difference. And so unfortunately, like if we were in class, I would be able to roll a die, and then we can actually count. Um, but the last time we did that, we got 3 out of 10. So it changes every time you conduct an experiment. So this would be an experimental probability based on actually rolling a die. Okay, but we're not going to be spending a lot of time talking about experimental probability because um, the numbers changes, right? So we are looking at something that's more consistent. So the last part is about a fair game. So if you did not know, the test for this chapter, I usually have a partner test for this chapter. So you're allowed to work with someone for the test, and I also let you know like what kind of questions will be on there, what you should know. This will be the first question about fair game. So it is kind of like the first thing you need to know about how probability works. So it says Sasha and Mika are inventing a fair game for a class project. So this is the game they're playing. Two people play. Each player has a container. They put 1, 2, and 3 into their container, and then they draw a number. Okay. So what you might want to do is to draw out the sample space of what could happen. So let's look at it together. We have 1, 2, and 3. Then 1, 2, and 3. Just a really rough sketch here. So this would be 1, 2, 3. Then 1, 2, and 3. Oops, that didn't look very good. There we go. Okay, it says here player 1 scores a point if the product is less than the sum, and then player 2 scores a point if the product is greater than the sum. So we're just gonna write down the sums and products. We're gonna write the sums in purple, and the product, let's write them in pink. All right, so the sums would be 2, 3, and 4, and then 3, 4, and 5, and then 4, 5, and 6. And then we're going to write the product. We have 1, 2, 3, 2, 4, 6. And then here we have 3, 6, and 9. Okay, so let's look at the scenarios under which player 1 wins. So you can see here that the player 1 wins in this spot, this spot, this spot. 3 is greater than 2, and 4 is greater than 3. So in all the orange check mark boxes, the sum is greater than the product. On the other hand, in these 3 boxes, the products are greater than the sum. And in the middle here, they tie. So nothing doing there. Just going to write in a neutral color. So you can see clearly that this is not a fair game because player 1 wins 5 out of 9 outcomes, whereas player 2 only wins 1/3 of the time. So this is not fair. So what you want to do for this kind of question is to write out the sample space like we did, and then figure out who is more likely to win. Or if it's like equal, then they're equally likely to win, and it's a fair game. This is not a fair game. So player 2 win 3 out of 9 probability, which of course you know is 1/3. You can reduce. So there's also like a way for them to draw as well. They will draw 1/9 of the time, but that doesn't really help player 1. I mean, sorry, player 2. So this game is not fair. Okay, so that's the main concepts for today. How to calculate kind of basic theoretical probability using sample space, and how do you determine if a game is fair or not. And that's it for today. So thank you for listening.